We have one more reaction to learn in this section, and this last reaction is called hydration. And once you get the hang of the hydrohalogenation reaction, the hydration reaction is going to be a piece of cake. So let's start, just like we did with the other three reactions, let's start by making a generic alkene. And again, we're not going to worry about what is attached to the carbons of the alkene. In this reaction, we are adding water, H2O, but instead of writing H2O, I'm going to write the water molecule like this, HOH, and you'll see why when we draw the products. This reaction does use a catalyst, so it's kind of like the first reaction that needs a catalyst, and remember the catalyst gets written underneath the arrow. The catalyst for this reaction is acid. It's usually sulfuric acid, H2SO4, but I'm going to give you a couple more formulas of acids that you could see in this reaction. And like the other three reactions, we're going to start by redrawing the molecule, converting the carbon-carbon double bond to a single bond, and leaving everything else alone. We're going to be adding two things to the carbons of the alkene. One of them is an H, and the other is an OH, and that is from the H2O. So that's why I like to write it as HOH. It helps us see the two parts of the water molecule. So the H2SO4 catalyst, you might see just H+, which is an abbreviation for H2O. Or you might see somebody write H2O, comma, H+. And so that's just those two different chemicals, the HOH and the H2SO4, just kind of written together. Or it's also possible that you might see H3O+. So you could see any one of those four different options for this particular reaction, which is one of the reasons why it's kind of tricky, because it'll come at you in a variety of different ways. So let's start with the same. Let me remind myself the alkene that we've been using for the first example for all of these. And just to get you used to seeing it in all kinds of different ways, I'm going to write H2O on top because it's plus H2O, and I'm going to write H+ on the bottom, like that. So we want to start by redrawing the original alkene, except the double bond is now a single bond. And we are going to add two things to the molecule, to the alkene carbon. One is an H and the other is an OH. This reaction, the hydration reaction, is similar to the hydrohalogenation reaction in that the two things that we are adding, the H and the OH, those are two different things. Just like with hydrohalogenation, we added an H and a Br, or an H and a Cl, or an H and an I. And that means that, again, we're going to need to use Markovnikov's rule to help us figure out which carbon gets the H and which carbon gets the OH. So the Markovnikov's rule in the hydration reaction is exactly the same as it is in the hydrohalogenation reaction. At least we have that much going for us. And let's practice a couple, and then let's go to the worksheet. This time I'm going to go, let's see, what should I do to try to make it different? I'm going to write H2O, comma, H+. So there's another way you could see this written. So what we're going to do is redraw the molecule without the double bond. We want to find our alkene carbons, identify them, and we need to figure out how many hydrogens were already on those alkene carbons. So the red carbon, if we go back to the alkene, we could see 3 of its bonds. That means it has 1 hydrogen. Let's draw that on the product. Our blue carbon, we can see 2 of its bonds, or two of its bonds, so that means it has 2 hydrogens, so we'll draw those in. Markovnikov's rule, we're going to put something here and we're going to put something here. Markovnikov's rule says the hydrogen that we add wants to hang out with all the other hydrogens. So we want to put our new hydrogen on the blue carbon because it has 2 hydrogens already, and that means our OH wants to go onto the red carbon. Let's do one more example and then we'll go back to the worksheet. This time we're just going to write H3O plus. So start by redrawing your alkene without the double bond. Find your alkene carbons. Figure out how many hydrogens were already on those carbons. So let's look at the red carbon first. We can see for the red carbon in the alkene, we're looking over here at the alkene, we can see 1, 2, 3, 4 bonds, so it has 0 hydrogens. Blue carbon, we can see 1, 2, 3 bonds, so that means blue carbon has 1 hydrogen. Let's draw that over here. Our new hydrogen is going to go onto red or blue, the one that has the most hydrogens already. Red carbon has 0 hydrogens, blue carbon has 1 hydrogen, so our new carbon goes with the blue, and OH goes with the red. Let's go to the worksheet. So these last 4 problems that we have, we're going to finish off this worksheet. We are going to start by redrawing the alkene without the carbon-carbon double bond. Find your alkene carbons. We're going to highlight them. And then look at the alkene and figure out how many hydrogens were already on those carbons. The red carbon, we can see 1, 2, 3 bonds, so that means it has 1 bond to a hydrogen. The blue carbon, we can see 1, 2, 3, 4 bonds in the alkene, so it has 0 hydrogens. The water molecule that we're adding is going to put 1 hydrogen onto the carbon that already has lots of hydrogens. It's going to go onto, the new hydrogen is going to go onto the red carbon. Oh my gosh, I did the same thing 2 times in a row. The new hydrogen goes onto the red carbon, and the OH goes onto the blue carbon. Next example. Well, let me highlight those, H and OH. Next example, redraw the alkene without the double bond. Find your alkene carbons. Color them, red and blue. Figure out, back in the alkene, how many hydrogens were on the red carbon. On the red carbon of the alkene, we can see 2 bonds, so it has 2 bonds to hydrogen. On the blue carbon of the alkene, we can see 4 bonds, so it has 0 hydrogens. Our reaction is going to add 1 bond to the red carbon and 1 bond to the blue carbon. It's going to add a hydrogen, and that hydrogen wants to go with all the other hydrogens. There is our product. 2 more to go. Redraw the alkene without the double bond. Find your red carbon. Find your blue carbon. Figure out how many hydrogens were on the red carbon. We can see 3 bonds on the red carbon, so that means it has 1 hydrogen. Figure out how many hydrogens were on the blue carbon. We can see 3, so that means it also has 1. This is a tie. This molecule is symmetrical, meaning that like it's kind of even right down the middle. When our molecule is symmetrical, it doesn't matter where we put the H or the OH. It's not going to make a difference. So we'll just go ahead and put the H up here. We'll put the OH down here. Maybe that stresses you out. You're not sure how to deal with that. In that case, You can imagine either scenario. These two molecules are exactly the same thing. And then we have one last example. So we're going to redraw the alkene without the carbon-carbon double bond. I want you to find your red carbon. I want you to find your blue carbon. I want you to figure out how many hydrogens you have on that red carbon. That red carbon in the alkene, we can see 1, 2, 3, 4 bonds, so it has 0 hydrogens. Then do the same for blue. Blue, we can see 1, 2, 3, 4 bonds. It also has 0. This is not a symmetrical molecule. There's no point like a middle or anything like that. It's not symmetrical. So that means where the hydrogen goes, where the OH goes, the hydrogen could go either on the red carbon or on the blue carbon. We don't have any kind of rules that are controlling where it goes. And that means we need to draw both possibilities. Both possibilities. And again, like I said the last time, this type of example right here is really, really hard. This last one is really, really hard. Most of the problems that you see are going to be much easier than that one particular example.